We have discussed some of the important topics of chiller operation. Let's look at a typical operational check. The purpose of the operational check is to analyze the operation of a system so you can properly diagnose any problems. This should be done on a periodic basis so that abnormal trends can be spotted early and serious problems avoided. A typical operational check consists of a job site visit, an interview with the operator or owner, an observation of the equipment, a comparison of current operating data to both the design or initial data and also to the preceding sets of data, and correction of any faults or malfunctions. Before the visit, you should obtain the necessary service and maintenance literature for the unit. Wiring diagrams are essential and will normally be found on the inside of the control panel door. Contact your distributor for any necessary literature and talk to your distributor service manager if you have any questions regarding the operational check. Have the following tools available at the time of the visit: an accurate gauge manifold set, volt-ohm meter, clamp-on ammeter, digital temperature probe, the correct refrigerant for the unit, normal hand tools, flashlight, trouble light. Now we're going to go through a typical operational check using a water-cooled nominal 100-ton chiller on air conditioning duty. The chiller we selected has a microprocessor control system. Many of the readings needed for troubleshooting are provided by a digital LCD display. Many chillers are not provided with this type of electronic display. If that's the case, the information will have to be obtained from thermometers and pressure gauges at critical locations in the chiller system. When we are called on to troubleshoot a chiller, it's usually because the chiller cannot make capacity. The first thing to do is to talk to the customer or operator and review the chiller's maintenance history. You'll need information about the chiller. Start by asking pertinent questions of what happened. Learn as much as possible. Specifically, when and how the problem occurred, at what point in the operation cycle did the problem occur, under what conditions did the problem occur, and what safety controls were activated. You also need to know the history of the chiller. Was there ever a freeze-up? Any plugged tubes? Was there a motor burnout or any other damage to the chiller? Most chilled water systems are equipped with gauges and temperature measuring devices at critical points in the system. It's essential to maintain a log containing such items as the chilled water and condenser water temperatures, the condensing and evaporating saturated temperatures and pressures, and so on. Here we see a typical recommended maintenance log. A copy is in your workbook so you can study it at your leisure. This is a record of key readings and services performed on the unit. A space is provided to record the design temperatures and pressures so comparisons can be made. The maintenance log is a valuable tool because by keeping careful watch on the log, you can detect developing problems before they become critical by comparing design conditions to the actual operating conditions. You should be able to find past log sheets on the job site. If no log exists, then a log sheet should be started. When starting a new log sheet, you will need to record the design conditions of the chiller. This design information should be available either at the job site or from the manufacturer's representative, such as the local distributor or dealer's office. If you cannot get design data, then use the data taken on the initial startup of the chiller as a reference. You will also need to record the actual operating system temperatures and pressures. For example, chilled water in and out of the cooler, condenser water in and out of the condenser, chiller suction and discharge pressures and temperatures, outside air temperature, suction and liquid line temperatures, and finally, amps and volts. For chillers with 2 refrigerant circuits, a set of data should be taken for each circuit. For the purpose of keeping this program comprehensible and focused, we will treat the chiller as a single circuit machine and will only use one set of data for our troubleshooting analysis. After taking the readings, compare the current operating temperatures and pressures with the design conditions and previous operating conditions to spot any trends which might be leading to trouble. Using the log sheets will help identify refrigerant side problems, including air in the chiller, low refrigerant charge, or water side problems, including dirty or fouled tubes, low or high GPM, and incorrect gauge readings. Now let's take a closer look at the log sheet and discuss each of the entries, starting first with the cooler section. Chilled water temperature entering the cooler. Prior to startup and during initial operation, this temperature will be above the design inlet temperature. Under stabilized conditions, this temperature should drop steadily until it reaches about 54 degrees Fahrenheit. Read and record the entering water temperature to the cooler. Chilled water temperature leaving the cooler. We also need to record the chilled water temperature leaving the cooler. After the chiller is placed in operation, this temperature should be within plus or minus 1 degree Fahrenheit of the design leaving water temperature at full or part load conditions. Design leaving water temperature at full load is typically 44 degrees Fahrenheit. Under extreme light load operation, this temperature could drop below design leaving temperature. However, a control sensing the water temperature, low water temperature cutout recycle switch will shut the machine down. It's not economical or good operating practice to operate a chiller under extreme light load conditions if other means, such as outside air, will accomplish the cooling job. Chilled water delta T. Now we can determine the chilled water delta T, which is the difference between the entering and leaving chilled water temperatures. Chilled water delta T provides an indication of system capacity. If it's above or below the design delta T, then a problem may exist. More about this later. Cooler saturated refrigerant temperature. A space is provided to record the cooler saturated refrigerant temperature. Under maximum heat load conditions, with the machine operating at design, this temperature should be at the design temperature. Under reduced heat load operation, when the compressor is running unloaded, this temperature will be above design. Under no circumstances, even at full load operation, should this temperature be allowed to drop below the design temperature, which is typically a few degrees above 32 degrees Fahrenheit. If the cooler saturated refrigerant temperature is at 32 degrees or lower, then the possibility of a freeze-up exists. If you cannot measure the actual cooler saturated refrigerant temperature, then the saturated temperature corresponding to the suction pressure may be used as the actual cooler refrigerant temperature. This temperature is required for determining the cooler leaving temperature difference. Suction pressure. Read and record the suction pressure. Refer this pressure reading to a refrigerant pressure temperature chart. Compare its correlating saturated temperature to the actual cooler saturated refrigerant temperature reading. These two temperature readings should be the same or at least very close to each other. Cooler leaving temperature difference, LTD. At this point, we can calculate the cooler or leaving temperature difference, LTD. This is the difference between leaving chilled water temperature and the saturated refrigerant temperature. This difference is also known as the cooler approach. Suction line temperature. This measurement is taken on the suction line near the suction service valve. Use a digital temperature probe to take this reading or read it at the control panel display if available. Record this temperature. Superheat. The superheat can now be calculated by subtracting the saturated cooler refrigerant temperature from the actual suction line temperature. On some units, the superheat may be read directly at the control panel display. Record the superheat. Chilled water flow. Space on the log sheet is provided to record the entering and leaving water pressures. The same gauge should be used to take both readings to ensure accuracy. The difference between the two readings indicates pressure drop, or delta P. It can then be compared to the design pressure drop to determine GPM. If a greater than design pressure drop is recorded, there's a possibility that the tubes are either dirty or the flow is too high. Pressure taps for taking pressure readings across the cooler should be as close to the inlet and outlet as possible and at the same height. If there's any difference in the height of the gauges, a correction will have to be made. We'll discuss this in more detail later in the program. Now let's look at the condenser section. Water temperature entering the condenser. This temperature should not exceed the design entering water temperature, and on most installations should not drop below 70 degrees Fahrenheit. Entering condenser water temperature can be up to 95 degrees. However, 85 degrees is more typical. If the entering water temperature drops too low, the condenser head pressure will not be high enough to supply refrigerant through the expansion valve. Water temperature leaving the condenser. This temperature will vary with the heat load and/or tonnage. Under full heat load conditions, it should not exceed design. Under less than full heat load conditions, the temperature will be less than design. Condenser water delta T. Next, we'll find the condenser water delta T. Do this by subtracting the entering condenser water temperature from the leaving condenser water temperature. Condenser water delta T provides an indication of condenser heat rejection. Condenser pressure. Record the condenser pressure. With design water temperature and water flow through the condenser tubes and operating at full heat load conditions, this pressure should not exceed maximum design condenser pressure. When condenser pressure is higher than design, it's an indication that the chiller is operating inefficiently. Condenser saturated refrigerant temperature. On some chillers, the saturated condensing temperature may be read directly at the control panel. If this is not the case, then the saturated condensing temperature is found by using a pressure temperature chart to convert the condensing pressure to a temperature reading. This temperature is required for determining the condenser leaving temperature difference. Condenser leaving temperature difference, LTD. The condenser leaving temperature difference, or LTD, is found by subtracting the leaving condenser water temperature from the saturated condenser temperature. This also may be referred to as condenser approach. Condenser refrigerant liquid temperature. Measure the condenser refrigerant liquid temperature. If a thermometer well or control panel display is not provided to do this, strap a digital temperature probe on the bottom side of the liquid line. Subcooling. The amount of subcooling can now be found by subtracting the liquid line temperature from the condenser saturated refrigerant temperature. Condenser water flow. Space is provided on the log sheet to record the entering and leaving water pressures. The difference between the two readings, or delta P, indicates a pressure drop of the water flow through the condenser tubes. The same gauge should be used for both readings to ensure accuracy. This pressure drop can be compared to the design pressure drop to determine GPM, and if greater than design, there is the possibility that the tubes are either dirty, plugged, or the flow is too high. Pressure taps for taking pressure readings across the condenser should be as close to the inlet and outlet as possible and at the same height. If there is any difference in the height of the gauges, a correction will have to be made. We'll discuss this in more detail later in the program. Air temperature entering condenser. Measure and record the outdoor ambient air temperature entering the condenser. This is a very important factor on air-cooled condensers because it provides a reference to what the condenser saturated refrigerant temperature operating conditions should be. Air temperature leaving condenser. For air-cooled condensers, this measurement will be useful in determining temperature rise across the condenser coil. The temperature rise, or delta T, can be determined by subtracting the condenser entering air temperature from the condenser leaving air temperature. The delta T provides an indication of the heat rejection by the condenser. Line voltage. Measure the incoming supply voltage and record each leg-to-leg voltage, 3 readings. Add the readings and divide by 3 to get an average. The average should be within 10% of the chiller nameplate voltage rating. If any one line voltage reading is more than 2% from the average, then contact the electric utility for correction. This condition is called phase unbalance, and it should never be greater than 2%. Motor amperage. Using a clamp-on ammeter, record the chiller's total motor amperage. But make sure the unit has stabilized first. It should operate at least 30 minutes before taking ampere readings. Check each power lead of the chiller. Then, total and average the readings. The individual amperage readings should be within 10% of the average amperage. Also, the average amperage should not exceed the design maximum. Compressor oil level. On most semi-hermetic compressors, either a sight glass or bullseye is provided in the oil sump to determine the oil level. The oil level should be within the sight glass. However, under certain operating conditions, a fixed oil level may not be visible due to the foaming of the oil. In this section of the program, we discuss the operational check, emphasizing the importance of a log sheet and explaining the data